The diagram shows a man standing in a lift which is moving up and down. So here we've got a man standing in a lift. Here's the cable of the lift. Draw a diagram showing the forces acting on the man and the lift. So let's just have a look at that first force. We've got the man. Okay, so we're going to have the weight of the man down. We'll call that W1 because we're going to have a weight for the lift as well, which we're going to call W2. And then there will be a reaction of the man standing on the floor of the lift, which we're going to call R. So the reaction of the lift is on the man. This is the reaction of the lift on the man. Right, the lift. So here we have the lift. We're going to have the weight of the lift, which we're going to call W2. We're going to have the tension in the cable. And then because the man's standing on the lift, there's going to be a reaction downwards of the man on the lift. Okay, so using these diagrams, we can now answer these questions. So write down the resultant force on the man and the lift if the lift is moving. B, so just draw the diagram again, upwards with a constant velocity. If we've got a constant velocity, then the system is what's known as in equilibrium. And therefore, for the man, we're going upwards, R minus W1 will be equal to 0, which will give me that R must be equal to W1. For the lift, okay, so we're moving upwards in constant velocity, so it's in equilibrium. We're going to have that T minus R plus W will be equal to 0, which is going to give me T minus R minus W2, or that T is equal to R plus W2. Part C, upwards with an increasing speed. Now, if the speed's increasing, we now have an acceleration, so Newton's second law starts to apply. So, for the man, okay, R will have to be bigger than W1 because the thing's going upwards. And then for the lift, the tension will have to be bigger than the reaction plus W2. D, upwards with decreasing speed. So what's going? It's still going up, but it's going to be decreasing. So now we're going to have, for the man, that W1 is greater than R. And that for the lift, we're going to have that R plus W2 is greater than the tension, the other way around. Okay, so here there's an acceleration, and it will probably be negative. Okay, here the acceleration will probably be positive. E, downwards at a constant velocity. If we've got, so for the man, we're going to have that W1 minus R is equal to 0, which means that W1 will be equal to R, not R1. So W1 will be equal to R. And then for the lift, we're going to have that R plus W2. R plus W2 will be equal to T. The system will be in equilibrium if we have a constant velocity. So quickly drawing those diagrams yet again. So downward with increasing speed, that means now that the man, that W1 will have to be bigger than R. This force will be bigger than R. And for the lift, we're going to have that R plus W will be bigger than T. R plus W, we're missing a little 2 there. R plus W2 will be bigger than T. And then downward with decreasing speed, these are going to be the other way around. We're going to have that R will be bigger than W1, and that for the lift, we're going to have that T is bigger than R plus W2. Okay, so it's been a video to show you how to deal with a man in a lift and looking at the resultant force on either the man and the lift. The secret is to draw separate diagrams for the man and the lift. I hope you've understood, and I thank you very much for watching.